Pluto is a remote and faint, more modest heavenly body that was once a component of our local star system. Despite being recent and shocking, statements by prominent space scientists Neil deGrasse Tyson and Michio Kaku have returned Pluto to public attention. They propose that this faraway object might be on a probable collision trajectory with Neptune. They're not just speculating, they're warning. This tiny world could be on a dangerous, direct path toward a catastrophic collision with Neptune. But how could that possibly happen, and what would the consequences be if such a massive event actually occurred? Are we witnessing some kind of bizarre cosmic illusion, or is something significantly more real and terrifying hurtling toward us? Pluto's orbit cuts alarmingly close to Neptune's. Neil deGrasse Tyson and Michio Kaku are sounding the alarm. If anything even slightly changes, we could be looking at a disastrous planetary mishap. Could Earth be in danger too? And more importantly, how feasible is such a cosmic event? Accompany us as we explore the potential ramifications of a Pluto-Neptune impact. Pluto, a former planet that continues to be classified as a dwarf planet, remains a topic of fascination in the expansive cosmos. As illustrated by current theories from experts in the field, Pluto's trajectory is dangerously close to Neptune's. Space experts Neil deGrasse Tyson and Michio Kaku are both sounding the warning regarding a possible dangerous relationship between these two worlds, one that has the potential to suggest a risk to Earth. Still, how might such a scenario be achievable? Pluto's voyage around the solar star is unlike that of any other celestial sphere in our planetary system. It requires an astonishing 248 Earth years to finish a full loop. Since its identification in 1930, it has yet to complete even one complete cycle. However, this does not end the curiosity. Pluto's trajectory is defined by its exceptionally elongated path, deviating significantly from the mostly circular revolutions of the principal planets. What makes Pluto's path even more extraordinary is its tilt, which is 17 degrees from the solar plane. The route Pluto follows is significantly more erratic in contrast with other planets. This tilt and eccentricity add layers of complexity to its orbital pattern. Arguably one of the most intriguing elements of Pluto's orbit is its overlap with Neptune's. For approximately 2 decades during each circuit, Pluto actually approaches the Sun closer than Neptune. Contrary to what one might expect based on their conventional planetary placements, this brings up the standard question: why hasn't Pluto collided with Neptune? The explanation resides in the gravitational influences of surrounding planetary bodies. The investigation of Pluto's path began shortly following its discovery. Initially, astronomical researchers attempted to comprehend its distinct route. Unlike most other planets whose orbits are relatively aligned with the solar plane, Pluto's route stands out due to its slanted layout and sharp angle. The enigma deepened with the understanding that Pluto's orbit does indeed intersect Neptune's. The steadiness of Pluto's path, despite these irregularities, stands as evidence of the subtleties of cosmic physics. The space's three-body conundrum involves understanding how a trio of cosmic bodies, such as Pluto, Neptune, and the Sun, move and affect each other through their gravitational pull. It's similar to predicting movements in the future based on original positions and mutual gravitational tugs. In Pluto's case, this issue demonstrates that its motion, Neptune's orbit, and the Sun's pull all operate in concert with one another. The expressions asynchronous oscillation, orbital drift, and VZK wobble are essential to unraveling this puzzle, as noted by astrophysics specialists. What maintains the planetary bodies in their circular tracks is asynchronous oscillation. Regarding Pluto and Neptune, this phrase fundamentally means that when Pluto passes through Neptune's orbital path, it is situated at no less than a 90 degrees angular distance away from Neptune. This angular separation is vital in preventing their paths from clashing. In contrast, orbital drift is the vertical motion of a body as it revolves. For Pluto, this indicates that when it gets closest to Neptune or another giant world, it lies significantly above their orbital tracks, providing an added level of defense against likely crashes. An additional major component in this discussion is the VZK wobble, named for 3 researchers, presumably Kaku, Zell, and Kai, who analyzed the spatial dynamics of cosmic entities. It involves how 3 astronomical masses like Pluto, Neptune, and the Sun exert pull on one another. Due to their widespread influence, this interaction shapes their movement. In Pluto's instance, the VZK wobble provides insight into why its route near the Sun appears to be so erratic. Despite Pluto's movement seeming unstable, this wobble aids in keeping it flowing smoothly across vast durations. The VZK wobble reveals that even though the cosmos may look chaotic and strange, principles and patterns still enforce some degree of order. These dynamics contribute to sustaining Pluto's steady path, making sure it doesn't crash into Neptune or stray from its regular route. This tri-body interaction is essential to grasping how space trajectories shift due to interjecting forces. Analyzing it teaches us more about Pluto, our group of planets, and even further away galaxies and their stars. Numerical projections in the late 1980s demonstrated that even though Pluto's orbit is reinforced by stabilizing attributes, it remains erratic. Small initial variances can produce dramatic divergences over centuries. Still, these orbital behaviors have been proven to maintain equilibrium over astonishingly extensive timelines. Evaluating changes via later automated readings has helped us learn how the behemoth planets, Neptune, Jupiter, and Saturn, affect Pluto's revolution around the Sun. Neptune shares a distinct orbital correlation with Pluto, which is the basis for Pluto making a turn every 2 revolutions while Neptune finishes 3. This synchronized relationship helps preserve Pluto's stability. However, Neptune doesn't act alone. Jupiter's immense gravity contributes heavily to keeping Pluto's track consistent. Saturn, as well, adds to the mix. Research reveals that Jupiter's colossal mass is powerful enough to protect Pluto's path from eventual extreme variations. It seems that Jupiter, Saturn, and Neptune are all working in harmony to guarantee that Pluto glides securely through the void without encountering hazards. These strange yet essential systems play a major role in the upkeep of cosmic order. Without such mechanics, our solar neighborhood would be a far more turbulent realm. Objects like Pluto might collide with others or be ejected entirely, causing domino effects with other astronomical entities, especially concerning Pluto and worries about its interactions with Neptune in the future. Understanding its motion is key. This offers a sharper image of the vibrant and ever-shifting nature of our planetary system. The example of Pluto shows how even seemingly unstable paths can reach balance via intricate gravitational and kinetic interactions. It also underscores the need for constant surveillance and scrutiny of such oddities to better comprehend our place in the cosmos. Probing deep into outer realms often makes us confront the bizarre characteristics of heavenly bodies. Furthermore, Pluto's orbit is a compelling testament to the layered intricacies of celestial mechanics. Its chaotic-looking course is, in fact, governed by deep and invisible harmonies of motion. Though it may appear as a cosmic anomaly, its behavior is a result of profound gravitational dialogues taking place over vast stretches of time and space. What this tells us is that the universe, though mysterious and at times seemingly unpredictable, adheres to rules that we, piece by piece, are beginning to understand. Pluto, once dismissed as an insignificant icy speck, now serves as a reminder that even the smallest bodies can hold answers to the grandest questions. As we continue observing the sky and refining our instruments, what other secrets might be waiting to reveal themselves? Could there be more celestial time bombs silently threading their way through space? Or are we simply witnessing nature's extraordinary balance at play? One thing is certain: the more we learn about Pluto, the more we uncover about the cosmos and ourselves. Stay curious, and keep looking up. A perfect instance of this anomaly, the theory of orbital disorder, which denotes the sensitive orbital dependence on starting data, is clearly visible here. This suggests that Pluto's minimal alterations in its coordinates or speed could greatly influence its far future pathway. Utilizing computer-based forecasting has proved extremely beneficial for space scholars working to decode Pluto's behavior. These programs employ elaborate equations to simulate how Neptune, Pluto, and other bodies work together and adjust to interact gravitationally. Within these forecasts, scientists can observe how even slight shifts can lead to completely altered destinations. In the latter part of the 1980s, such digital models revealed a surprising insight. Despite the fact that Pluto has stabilizing mechanisms like asynchronous oscillation and orbital drift, its journey may still behave abnormally. If Pluto begins with just a tiny discrepancy in location or velocity, its position in the future may appear enormously different in only a few years. Yet despite this unpredictability, Pluto's trajectory has endured across immense spans of time, spanning billions of years. That means Pluto's path has an underlying consistency, despite seeming unruly at first glance. Predicting stellar orbits, particularly ones as erratic as Pluto's, remains a monumental task. The core unpredictability of these systems results in far-off predictions that are rife with unknowns. Although models built on math are outstanding for decoding and estimating cosmic motion, they also highlight our limits. These formulas depend heavily on starting values, and even the tiniest error or modification can shift the result dramatically, making pinpoint accuracy a real challenge. Beyond the erratic tendencies of planetary pathways, Pluto highlights the constant evolution and flux of the universe. Although humanity has uncovered significant knowledge about the stars, the oddities of Pluto serve as a reminder of what still lies in the shadows. Deciphering how massive planets alter Pluto's movements grants us broader awareness of solar system behavior. It shows how each planet's presence and place can meaningfully influence the steadiness and direction of others within the structure. So why are notable astrophysicists suddenly expressing anxiety about a possible smash-up between Pluto and Neptune, even with all the cosmic laws acting to prevent it? Neil deGrasse Tyson, a well-known space scholar and a key promoter of cosmic knowledge, delivers a distinct angle on the mysteries of our planet. Tyson recognized Pluto's peculiar saga. For his efforts in demoting Pluto to dwarf status, he provides perceptive thoughts on the shifting principles of orbital research and the general public's fascination with overlooked areas. His position regarding Pluto's label in the heavens stems from our constantly improving understanding of the solar neighborhood. He views the shift not as an insult, but as a critical correction to our grasp of objects revolving around our star. Tyson's outlook on orbital physics emphasizes continual education and flexibility. He interprets complicated trajectories like Pluto's as a symbol of how much more there is to uncover. The mystery of such questions keeps astronomy exciting. But while Tyson remains hopeful, his outlook on a potential Pluto-Neptune collision is far less cheerful. His apprehension about the future of Pluto, when it was a full-fledged planet, is rooted in his recognition of the erratic behavior of these orbital dances. He acknowledges that Pluto has so far remained safe, but minor modifications accumulating over time might trigger disastrous events. Pluto's trajectory, particularly its overlapping zone with Neptune, forms a complex spatial rhythm that may not remain in sync forever. In Tyson's perspective, even the slightest disturbances in Pluto's path could yield huge repercussions. If these imbalances persist and grow over millennia, they could eventually result in chaos, or even a planetary crash. But such a development wouldn't happen in the near future. Instead, it would span unimaginable lengths of time, well beyond the reach of Tyson's human civilization. His cautious tone calls for further vigilance and more in-depth research into Pluto's orbital pattern. Tyson isn't standing alone. Michio Kaku, a renowned theoretical physicist, also ponders the astronomical upheaval that might result from interplanetary interactions. Although Kaku matches Tyson's awe for the majesty of the universe, he also recognizes the shaky balance of planetary orbits and the wild, unforeseen effects that may arise with time. Both Kaku and Tyson highlight the necessity of persistent space exploration into the invisible powers dictating planetary drift and the outlook for our starbound family. In the end, Pluto's situation exemplifies how our understanding of the universe is fluid, always adjusting. Each breakthrough leads to further intrigue. As space science progresses, the slim possibility of a Pluto-Neptune collision is a humble reminder of how vast space is, filled with unexpected turns, and how even peaceful planetary paths can change drastically over time. These lessons from Pluto serve to remind us to keep an eye on the skies and to keep pondering the secrets that the stars still hold. As telescopes grow sharper and artificial intelligence begins to play a larger role in cosmic calculations, the boundaries of what we can predict continue to expand. Yet, with every advance comes a reminder: the universe doesn't easily give up its secrets. Each new insight into Pluto's behavior opens doors to deeper questions, not just about one icy world, but about the gravitational choreography of the solar system itself. Pluto, once relegated to the edge of our planetary family, now stands as a symbol of how much lies beyond traditional definitions. Its complex orbit, relationship with Neptune, and historical controversies all serve to remind scientists and enthusiasts alike that our understanding of space is ever-evolving. Just as continents shift and stars are born and die, the status and interpretation of celestial bodies can change with the times, and with the tools we use to study them. The deeper we delve into the outer solar system, the more we uncover about the resilience and fragility of planetary systems. Seemingly minor details, minute gravitational tugs, subtle variations in speed, can scale into forces powerful enough to reshape orbits and rewrite expectations. Pluto's ongoing dance with Neptune may appear graceful and balanced today, but the future remains unwritten, woven with variables still unknown to us. That mystery, as Tyson and Kaku suggest, is not a flaw of science but one of its greatest assets. It fuels curiosity, drives innovation, and compels humanity to keep looking upward. In a universe governed by both elegance and entropy, even the coldest, most distant dwarf planet can spark some of the warmest debates and grandest inquiries. In the years to come, missions may yet reach Pluto again, carrying more refined instruments and more ambitious goals. They may map its terrain with higher resolution, track its movement with unprecedented precision, or discover new clues about its past, and possibly its fate. But even if a Pluto-Neptune collision never comes to pass, the mere possibility of it urges us to understand not only what is, but what could be. Because in the grand scheme of the cosmos, even long odds are worth the watch.